Thank you very much. So in the previous talk, we heard about how we can make MRI more efficient by removing unnecessary sequences. And the idea of the second talk in this session is to look at new acquisition principles that also might help us to make MRI more efficient. And what I want to do is I want to use the first minutes to talk about a project on workflow analysis, because I thought that this could be interesting in this context. And then based on that, I want to discuss why I think we should change the way we are doing MRI. And then in the main part of this talk, I want to discuss a few concepts that might help us to make it more efficient. And then at the end, I want to quickly touch on the question how we can get this into reality. So I'm a basic MRI researcher, and I became interested in the clinical side of MRI mainly through a project that we recently did in our department. And the goal of this project was to identify inefficiencies in our workflow, implement changes, and then to quantitatively monitor how these changes improve our workflow. And to do this, our clinical collaborators approached us and asked us if we can develop a software solution to support this. And so that's what we did. We developed a software that allows us to automatically monitor all our MRI scanners throughout the day and to collect data what they are doing throughout the day. And then the software provides very flexible functions for working with this data and for analyzing the workflow data. And a further requirement was that we also wanted to connect the system to our scheduling system and our dictation system so that we can also take advantage of this data. And the reason why I want to show this here for a minute is that we are making this solution available as an open source software package. It's part of our Yara Reconstruction framework. And how it basically works is we have a small software running on all our MRI machines. And every hour, this software sends the information about all scan sequences to a central server in our network. And on the server, we have a small application running that receives all this information. And it's then aggregating the sequences into examinations, and then it's storing everything in a database. And we are using a standard SQL database here, and therefore we can then use different tools to work with this workflow data. On the one hand, it's possible to use standard business intelligence tools, but we are mainly using a web-based solution called Redash that allows us to very easily create different dashboards and visualizations of the workflow data. So in this way, we can now automatically monitor what the activity of our scanners is throughout the day. What we don't get from the scanners is the information how long it takes to prepare the patient. So how long it takes to set up the coils and how long it takes to set up the power injector. And also to get this information, we developed these buttons that we installed at our scanner doors. And it's a very simple workflow. Basically, you press the button when you take the patient into the scan room. And then you press the button again after the scan when you take the patient out of the scan room. And these buttons are Wi-Fi connected, and they are then automatically sending this information to our server, and it's automatically assigned to the patient. And in this way, we can now also very easily measure what the room time is, and from that, we can then calculate what the preparation time is. And in addition to that, in our new outpatient center, we are additionally tracking the patients using such RFID wristbands, and this information also feeds into the system. Now, to work with this data, you have to log into a website. And here you can first see which scanners are being monitored and what the status is of the scanners, which software version is running on these scanners. And then if you click on one particular scanner, you can see the schedule for a certain day. So you can see which examinations have been performed on this day. And the color here encodes what kind of examination this was. So red means it was a neuroscan, yellow means it was a cardiac scan, and blue would be a body scan. So if you hover with the mouse, you can see more detailed information about these scans. And then these black bars around the examinations indicate when the patient was inside the scan room. If you then scroll down, you get the same information in a table. And if you click on one particular exam, you get detailed information about this particular exam. And you can first see a summary here that shows you how much time of the examination time was actually scan time, how much time was adjustment time, and how much time was dead time. If you then scroll down, you can see which imaging sequences have been acquired, and you can see how long the acquisition took. And if you further scroll down, you get a detailed timing diagram that shows you in which order this examination has been performed. So these blue bars here are the adjustment scans, then this yellow bar here, this is a localizer scan, and these green sequences are the different imaging sequences, and of course the white space in between, this is dead time. So this is the amount of detailed information that we get for every examination. But the really interesting part is that we can take this data that we get and we can aggregate it and create different statistics. And we can create all kinds of different dashboards. This, for instance, is a dashboard that we created for our chair. that allows him to compare the performance of our different scanners in terms of scan efficiency and transition times. If we want, we can break this down by imaging protocol, or we can look at transition times and how the transition times depend on the type of transition. And then we can also create very specific dashboards. So this is an example here. This is a dashboard that looks only at our liver examinations, and then it's calculating how long the DCE component takes when you include the breath hold commands and the timing run. And so using this tool, we are now able to analyze hundreds or thousands of examinations with a single mouse click, and we can then answer such questions. And I think that that there are many applications for this tool. So we are using it a lot at the moment to try to see if we can optimize our scheduling strategy. It's very helpful as a diagnostic tool because you can always look back at how a certain examination has been performed. And it's also very useful to track research studies. And if you're interested to learn more about this, we have a website, and I'm also happy to show this afterwards. Yeah, and for me personally, this tool also helped me a lot to much better understand the clinical side of MRI. And for me, as a basic scientist, I have to say that I totally underestimated how complex and how complicated clinical MRI is. And here are just two examples that I took from the workflow tool. So this first example here is a pelvis study. And this study had 44 different imaging sequences. And if you include the adjustment scans, it's actually 130 scans. The second example here is a cardiac study, and in this case, there were 40 imaging sequences, and actually 43% of the examination time was dead time. And this means in 38 minutes of this examination, no valuable data has been acquired. So there are two things that you can see here. First of all, we have lots of sequences, and we have lots of dead time. And because there are so many different sequences, you really need to be an expert to know when to use which sequence and how to use these different sequences. And I think that that's something that really developed over the years. I think in the early years of MRI was a pretty simple to use tool where you had a few sequences, and these sequences had clearly defined applications. This is how I think about MRI today. Today we have this zoo of different sequences that basically allow you to do everything with MRI, but it's very complex, very complicated, and very difficult to use. And I think that this high complexity really creates a lot of confusion. And it's not just creating a lot of confusion. I think it's actually creating a hesitation to use MRI because it is too complicated. And adding to this complexity is that these sequences are configured using a large number of sequence parameters. And for the fun of it, I took a screenshot tool and made a copy of every sequence parameter for only a single sequence. So all these sequence parameters that you can see here are coming from one imaging sequence, and I counted over 150 parameters per imaging sequence. Now, 150 parameters per sequence, we know from the workflow tool that we do about 12 imaging sequences on average per patient. And we have in our department 324 different imaging protocols. And this is only clinical protocols. This does not include research. And in our department, we have about 50 MRI scanners. And if you add this up, you end up with 29 million parameters that have to be set to the correct value. And if one of these parameters is incorrect, then one of these examinations might go wrong. And this is creating an enormous maintenance effort because you need to make sure that all these parameters are correct across all your MRI scanners, and it's creating an enormous training effort because you need to teach your people, you need to teach the staff which parameter to change if something is wrong with the images. And it's just inherently prone to human error. And I don't understand why it has to be so complicated. I mean, today we completely understand MRI physics, so we know what's going on inside the MRI scanner, and an MRI scanner is a relatively simple device. Simple in the sense that it hasn't changed much over the last 20 years. It's basically a 5-channel sequencer, and all we have to do from the sequence development side is we have to switch waveforms at certain time points. And I think a problem is that conceptually we are still thinking of an MRI machine as some kind of scientific experimental device. Pretty much like these old NMR spectrometers that had a lot of different controls, and these controls allow you to configure your experiment, and then you would execute your experiment. And in a way, the workflow has never really changed from this old paradigm. You set up your experiment parameters, and then you run the experiment. And I think we should move MRI forward. I don't think that it's necessary anymore today that we are exposing the internal MRI physics to the end user by showing all these parameters. And I think that a modern MRI scanner today should be able to determine the best parameters automatically. Pretty much like a modern digital camera, if you have such a modern digital camera, you press a button, and then the camera automatically determines the best exposure time, and it will always give you a good picture. And I think that we need something like that also in the MRI world. So this is the vision. Unfortunately, the reality is in MRI, we are still in the age of analog photography, where we have devices that have a lot of different controls. And if you have a lot of training and you're an expert and you know how to use this device, then you can make great pictures with this. But if you have to be time efficient and if you want to be consistent, then this is what you want. And I think a further mistake that we've been making is that we are too much thinking in terms of generic technical sequences. A single sequence cannot give you optimal results across all applications, and that's why we have all these parameters these days. And I think that's the wrong way. I think we should go away from that and move towards more intelligent imaging solutions that are tailored for specific applications. Pretty much like what you have in digital photography. So if you take a modern digital camera, you have these different scenes, and by selecting a scene, you're telling the camera, hey, now I want to take an image of a sunset. And by selecting the scene, you're narrowing down the application. And by narrowing down the application, the acquisition becomes a simpler problem. And it's also possible then to have a simpler imaging workflow. And I think that we should do something similar also in the MRI world. And so in the next part of this talk, I want to discuss a few ideas how we could do that, how we can simplify the acquisition by focusing on a certain application, and how it will be possible to have a simpler examination workflow. And I want to stay for a moment with the comparison to photography, because the way we do MRI examinations today is pretty much like a photo shooting. We are sequentially acquiring a number of still images. So each time we ask the patient to hold still, then we take a picture, then we look at the picture if the picture is okay or not. If the picture is okay, we go to the next pose, and if the picture is not okay, then we repeat. And this is, of course, not very efficient. And in addition to that, it only works if the patient is actually following these instructions. And that's a particular problem if you want to image the abdomen and the chest, because here patients need to hold breath on command. Now, the reason why we need to give these instructions is that MRI is conventionally very sensitive to motion. And this is coming from the sampling scheme, how we conventionally sample the data space, which is in a row-by-row fashion, also known as phase encoding. And phase encoding is very sensitive to creating these ghosting artifacts that can easily render your images non-diagnostic. And what's interesting is if you go away from this convention that we have to sample the case space in a row-by-row fashion and allow different sampling geometries like spirals or radial, we are automatically becoming much more robust to motion. And it's actually so robust that it becomes feasible to acquire data while the patient continues to breathe. And this means we don't have to give these instructions anymore, we can just scan. And what's interesting is that this is a very old idea. This is known for many years, but only recently it found its way into clinical practice. So the first idea here is to go away from phase encoding and use non-Cartesian sequences instead, at least for some of the applications. And instead of giving instructions, you just start the sequence and let it run. And these non-Cartesian sequences usually take a little bit longer. They are not as fast. But since you don't have to give these instructions anymore, and since you potentially have fewer sequence repeats, you can save examination time. Now, a particular type of examination where these instructions play a particular role or a big part of the examination is dynamic contrast enhanced imaging. And in particular, dynamic contrast enhanced imaging of the abdomen. So if a patient comes in for a liver examination, what you conventionally do is you first acquire a pre-contrast image, then you give a little bit of contrast to do a timing run, then you give the actual contrast, and then you have to acquire images at certain time points after the injection. And it's very important to follow this exact timing scheme because that's kind of your diagnostic information. And of course, conventionally, these scans have to be done during a breath hold. And this really makes this examination very difficult because now the technicians have to give the breath hold commands at the right time, and the patient has to hold breath at the right time. And the problem is if the patient does not do a breath hold, then the whole examination can be useless because you can't repeat the scan. Once you inject the contrast, you cannot repeat the scan. And therefore, we were thinking of whether there's a way of simplifying this examination with the use of such a non-Cartesian acquisition. And the idea that came up was, instead of doing these separate scans with dead time in between, how about we just scan all the time? Use a non-Cartesian sequence, scan all the time, And while this continuous acquisition is running, we just inject the contrast agent. And then afterwards, we can take this continuously sampled data, perform a time-resolved compressed sensing reconstruction, which gives us a time series of images where you can see how the contrast goes into the body, and then you can simply pick those time points that are needed for making the diagnosis. And this is a method known as GRASP, and GRASP really leads to a significant simplification of the whole workflow, because now we are now sampling the data continuously, and this means it's impossible to miss one of these enhancement phases. And this also means that we don't have to give a test bolus anymore and do a timing run, because we don't really care about the recirculation delay. And also, you don't have to give breath hold instructions, because it's based on a radial acquisition, so it works during free breathing. And what this means is that this previously very complicated examination that required a lot of trainings of the technicians now becomes a simple one-click procedure. Now, in addition to simplifying the workflow, GRASP also offers new possibilities for flexible reconstruction. So what you normally do is you take your continuously sampled data, and then you group a certain number of views into one image so that you get a time resolution of about 15 seconds. So specifically in this example here, if you combine 89 spokes into one image, you get a time resolution of 17 seconds. And this is good enough for for making your diagnosis. But what's interesting is you can take the same data set here and reconstruct this data set again using a different number of spokes. And if you combine only 8 spokes into one image, you suddenly get a time resolution of 1.5 seconds. And this means you're now getting perfusion information, which potentially allows you to learn something about the organ function. So you're doing one acquisition here, you're running 2 different reconstructions, and you get 2 different kinds of information. You get dynamic images and you get perfusion images out of the same acquisition. So the second idea here is to go away from these separate scans towards a continuous acquisition where you try to get as much information as possible. And this, of course, results in a better utilization of the MRI scanner because you're scanning all the time, and it also leads to a simplification of the examination workflow. And in addition to that, you can also get more. You can also extract complementary information. Now, one kind of information that you can additionally extract from the data is to get respiratory information. So if you do a continuous radial acquisition, for instance, from the case-based center information, you can extract such a respiration curve that tells you how the patient was breathing while the data was acquired, and you get that for free from the data. And then you can take this respiration curve, you can bin it into different breathing states, and then you can take your data and you can sort your data depending on the motion state. And by sorting it, by sorting the data according to the motion state, you're getting a new dimension of your data set which corresponds to different motion states. And you can then reconstruct along this newly sorted motion dimension, and in this way you can spatially resolve that motion. And here's an example that illustrates the advantage of such a motion-resolved reconstruction. This is a chest scan that has been acquired during free breathing, and because the scan time was around 8 minutes here, you get motion blurring. But then by performing such a motion-resolved reconstruction, you can spatially resolve the motion and you can clean up the images and you get sharp morphologic images. But in addition to that, you can also play back the images along the motion dimension, which is shown here. And so by playing back along this motion dimension, you can now see how the patient is breathing, and this then gives you functional information about the lung. So you get information about the lung function. So again, you do one acquisition and you get 2 different kinds of information here. You get morphologic information and you get functional information. Now, if you want to use this idea for cardiac imaging, you can even push this further. When you do a cardiac scan, you can get a respiratory signal, but in addition to that, you can also extract a cardiac signal. And you can get these 2 different motion curves by looking at different coil elements. And once you have these 2 different curves, you can then take your data and sort your data into a 2-dimensional array, where one dimension of this array corresponds to different respiratory states, and one dimension corresponds to different cardiac states. And you can then reconstruct these different motion states. And what this then allows you to do is you can do a free breathing acquisition without any ECG gating, and you can then retrospectively virtually create a breath hold by playing the cardiac motion at a fixed respiratory state, which is shown here in the middle. So this data was acquired during free breathing, but now you're stopping the respiratory motion when you're looking at the images, and you get a CNS scan that looks like it was acquired during a breath hold. And of course, you can also turn things around. You can stop the cardiac motion and play back the respiratory motion and look at how the heart is deformed as a result of the respiration. And this is shown here on the left side. So this actually is a new kind of information that you can get by performing such a motion-resolved reconstruction. Now, this is data from Li Feng and Ricardo Otazo, and the group of Matthias Stuber in Lausanne then extended this principle to volumetric acquisition. And for this volumetric acquisition, they used a radial 3D Couche-Ball trajectory. And this radial Couche-Ball trajectory gives you isotropic spatial information. And this means you can retrospectively generate any desired image orientation from this 3D data set. And this then means you don't have to pre-select your image orientation and image plane while the patient's in the scanner. You can just scan. And this also means it eliminates all planning steps that are conventionally needed for identifying the right imaging planes. So instead of running a number of localizers to find the right image orientation and then sequentially scanning in different orientations, and of course each time you need to perform a breath hold, or the patient has to perform a breath hold, instead of doing that, you just do one continuous acquisition during which the patient is breathing normally and without any ECG gating, and you can then retrospectively generate any desired image orientation from this comprehensive data set, and you can look at myocardial function in different orientations, or you can look at neighboring structures like the aorta, both in a static view where you're stopping the motion, as well as in a functional view where you're playing the cardiac motion. And you can look at aortic root, you can look at pulmonary arteries, and you can even look at the coronary arteries, both again in a static view where you get morphologic information, as well as in a dynamic view where you get functional information. And you can not just get functional information, it's also possible to get additional contrast. This is recent work from Thomas Bankert, where he used a radial continuous multi-echo sequence. And in combination with a model-based fat-water separation, it's then possible to get a water-only image, a fat-only image, an in-phase image, and a post-phase image, all from a single continuous free-breathing acquisition. And if you want, you can push this further. It's possible to additionally integrate a T2-weighted 3D FSE train. And this means you do one sequence and you get 5 different image contrasts out of that single sequence. So all these contrasts are coming from a single sequence. And if you want to, you can also combine this with motion-resolved reconstruction so that you can even look at the different breathing states. So all the images shown on this slide come out of a single sequence. And this means you have to run fewer different sequences. So the last idea here is to do a comprehensive acquisition where you try to encode as much information as possible into a single scan, and this then allows you to consolidate your sequences. And a nice feature of this idea is that you can retrospectively extract the desired information. And this really means that there is a shift of the imaging paradigm. You don't have to pre-select everything while the patient's in the scanner. You can just do your acquisition there, and then in the reading room, you can retrospectively pull out the information that you're interested in. And this also means that fewer things can potentially go wrong in the exam room. And if you think this idea further, it will, of course, bring you to the idea of MR fingerprinting as pioneered by the Case Western group. And here the idea is now that you're doing a continuous incoherent acquisition. And these incoherent acquisitions give you these highly undersampled images. And from these highly undersampled images, you can then generate quantitative maps of the underlying physical properties. And from these quantitative maps, you can then retrospectively generate any desired image contrast. And this means while the patient's in the scanner, you don't have to think about which image contrast you want to acquire. You just scan, and then you generate your contrast retrospectively. One final word on data processing. So all the ideas that I discussed here have in common that they all create very large, multidimensional data sets. And unfortunately, most of the software tools that we have available today are not able to handle these large multidimensional data sets. And here's an example. This is time-resolved MRI acquired with radial continuous acquisition. We are doing these scans quite a lot in our department because they are very simple to do. You just start the scan and you inject. But each data set creates, or each acquisition creates 28,000 images. And most DICOM viewers will simply crash if you try to load such a data set. And so for these novel acquisition techniques to really become clinically usable, we also need tailored software tools that actually make it easy to work with this kind of data. And I think this is a very important point, because if the data processing takes too much time, then we are losing all the efficiency that we are gaining in the examination room, and in the end it would be a wash. So it is important to also look at the data processing side. So to summarize that, I think we should go away from the idea of the classical idea of the NMR pulse sequence and move towards more comprehensive and more intelligent imaging solutions. And these comprehensive solutions should start with some kind of comprehensive acquisition, but also include a matched reconstruction and data processing and reporting. And I think we need the whole package here, which to me is an exam app. I think we should move away from sequences towards exam apps. And by having such disease-specific exam apps, I think it will be possible to have a much more streamlined and a much more time-efficient examination workflow. So there are lots of ideas, and in the last few minutes, I want to discuss how we can get these exam apps into reality. How can we get there? And so on this picture here, you can see a mobile MRI unit outside of our department. This mobile MRI scanner has been installed after Hurricane Sandy destroyed some of our MRI scanners. And the MRI scanner that's inside this truck is actually 15 years old. And what I found quite interesting is that this 15-year-old MRI machine still provides state-of-the-art imaging. The images look great, it's very reliable, the technicians love the system, and we are doing all kinds of examinations with this device. And really the only reason why we are removing this MRI scanner is that it's blocking a New York City walkway. And I found it really interesting because it's so old. But what this shows to me is that there's a growing disconnect between what's happening in basic MRI research and what's actually arriving in clinical practice. So in basic MRI research, we have all these new approaches, continuous acquisition, compressed sensing, but it doesn't really arrive in the clinic. And why is that? And in my opinion, it's the consequence of the traditional academic dissemination model that we have in the MRI world. So for many of us researchers, what we actually do in our daily work is we develop a piece of software, be it a sequence or some new reconstruction algorithm. And then we take the software, we run a number of experiments, and then we publish the results by writing a scientific publication, or if it's very promising, then maybe we also file a patent. But this is really where our work ends. And then we have to wait, and we have to hope that somebody in industry will find this and try to reproduce this, and hopefully they will reproduce it correctly, and then hopefully they decide to integrate this into their next scanner generation, and then they have to sell the system, somebody has to buy the system, and finally in this way our development arrives in the clinic. But this is of course not very efficient, and in particular there are two bottlenecks here. First of all, the bandwidth of the industry developers is limited, and at the same time our approaches are more and more complicated. And the second bottleneck is here. Modern MRI systems have a pretty long lifespan. And therefore, it really takes a long time until new innovations propagate into the clinic. And it really takes a long time until there's a sufficient market share. And it would be so much more effective if we could go the direct way, if we could directly disseminate our developments into the practice, or into the clinic. But unfortunately, that's not possible at the moment. And I think that's really a problem that we need to tackle. And in my opinion, the possible solution would be to have an open development platform that really makes it possible for third parties such as universities or startup companies, to independently develop solutions, but not just to develop solutions, but actually to disseminate these solutions into the clinic, maybe by having something like an app store for these exam apps. And it actually wouldn't take too much to do that. There's basically two things that we need. First of all, we need documented and reliable scanner interfaces, which we don't have at the moment. And we need a legal foundation that actually makes it sustainable for developers to invest time into the development of such solutions. But if we look at the mobile industry, and if we look at what happened in the mobile industry when the vendors decided to open up their platforms, it was a real game changer in the mobile industry. And of course, MRI is different from the mobile industry, but I believe that it would be also a game changer in our industry here, because by having an open development model, it would for the first time create a real incentive for researchers to make the step into clinical practice. There would be really an incentive to push developments into clinical practice. And we do have a large community of MRI researchers, and therefore I believe it would result in a tremendous gain of development power. And there would be so many advantages. You could have much more specialized applications that would not be profitable for the big vendors. You could think about new payment models like pay-per-use. And lastly, this would be a way to continuously deliver innovations to these installed base systems instead of just waiting for 15 years until they get replaced. Now, unfortunately, the big vendors are not yet seeing the advantages of such an open development platform, but in my opinion, it's really a missed opportunity because locking up the systems really means locking out innovations. And I think, therefore, we really should have an ongoing discussion, not just with the vendors, but also with regulatory authorities and also with funding agencies, because if all we do in our research work is develop stacks of papers that don't really add value to the patient, then people might ask at some point, what's the value of doing all this MRI research? But if we can change our development model in a way that our developments actually arrive at the patient in reasonable time, I think we can bring MRI to a new level and make it a much more valuable modality. Thank you.